Okay, folks, we will be talking about distributed forces, centroids, centers of gravity. So why do we worry about how forces are distributed? Well, okay, so previously we've been talking about point loads, concentrated loads, so on and so forth. The problem with those is that they're not a real thing. Anytime you have some sort of force, it is going to be distributed over an area. Even if I take my pen here and jab it into my hand, that force is being concentrated into a very small section of my skin, but it is distributed over that area, even if the area is small. Probably the closest thing that we get to an actual point load would be, say, the force of gravity on a particle. Not even on a molecule, and not even on an atom. If you get the force of gravity on a proton, or the force of gravity on a neutron, then that I think would be a point load. But again, that's not really all that useful. So we often find it easy and convenient to do our math if we represent various distributed loads as point loads. And the way we do that is basically figure out what the total force of that load is and find out where we can place it such that there wouldn't be an equivalent moment. So I think most of you are probably familiar with the concept of a center of gravity. So essentially, gravity exerts a force on each particle in a body. And if you take up all the sums of those forces on all those particles, you get the weight of the object. But you're also going to get what we call a center of gravity, and that's basically taking up all of the little individual components. Instead of this thing with a large mass, instead we look at all the tiny little forces from gravity of each individual particle, each individual little block. We kind of add all those up. We add all those up, and essentially, when we add up all those tiny little bits from each particle, we get the total mass, but we also get a location at which it acts. So it acts at the center of gravity. And essentially what we're saying there is if we take the moment of all of these individual forces that make up the total weight of the object, if we take all of those billions of little moments, take all those billions of little forces and take a moment about the center of gravity, then that moment will be zero. It'll all add up zero, regardless of kind of the orientation of the object. So that's a physical location in an object, or sometimes it's not necessarily within an object, but in relation to an object. For example, the center of gravity of this ring, my wedding ring here, it's located in the middle of the empty space inside the ring, but it's in relation to the object itself. So anyways, we can add all those up and pretend that the weight of the object is a single force acting through that point. And then we can do stuff like, say, balance the thing on a pencil as long as the pencil is placed at the center of gravity. It'll be in equilibrium at that point. So the annoying math. So basically, for a 2D body, what we want to do is, if we take our object and split it up into a whole bunch of tiny little cubes, what we can do is we can find the centroid of the object times the weight of the object is going to be equal to, I realize that top of that got cut off there, it's going to be equal to the integral of, the integral of x times the tiny little cube of weight. So we're breaking up this thing into tiny little cubes, multiplying each of those cubes by its distance from the y-axis, and then adding all of those up in an integral. So that's this is what we call the first moment of area, with regards to y here. So that if we're talking an object that has a uniform density, then essentially this becomes we basically, and if we're talking a plate, then the thickness, the weight is going to be equal to the volume of the object times its density. So we can break the volume up into its thickness and its area. We can kind of just factor out the thickness and the density portions, because those kind of assuming that if we're talking a 2D body, then those don't vary at all. So this becomes a matter of the area, and it becomes a geometric function. So that allows us to get the first moment of area. So we can do that we can get our x bar A or our y bar A. That'll be our first moment area with regards to y, or first moment area with regards to x. And we can do something similar to we can do something similar if we're working with not a plate, but some sort of a wire. We can break it up into chunks of length instead of chunks of we can break that weight up into chunks of length, and instead we kind of treat it. In either case, we can kind of treat it as if we're only worried about the area, or only worried about the length. So we can. This is essentially us taking the previous page and making the assumption that this object is perfectly flat and has uniform density. So then we're worried about the centroid of this area, and essentially once we kind of do this calculation, we can find the location of the centroid by dividing by the area. Similar idea for the line. Same idea. We're just worrying about the line itself. We're worrying about the length of the individual length components of the line, and the x locations at that point. Same here with the y. And then do that integral, divide by the total area, we get our location of the centroid. Same deal with y. Is it up a little bit there? Okay, so here we've got a few common centroids. Here, I think I zoomed it. There we go. I zoomed in a bit too much down there, didn't I? Okay, so some common centroids. Stole this from your textbook, except for one thing I had to add myself. The location, the x location of a of a triangle is just basically taken from any point. It's just the it's the average of the x of the location along the x-axis of each of the corners. I don't know why they didn't include that in your textbook. Feel free to go ahead and add that. That'd be great. To the end, just x1, x2, x3 divided by 3. So again, if we've got a right triangle, it's just located at 1/3 the distance of the base here, because basically that's us using this the 90-degree angle as the 0, and then so 0 plus 0 plus b for our base divided by 3 gets us b over 3. Same deal with the height. The y bar location works out to the same thing as long as the bottom base here is flat. And then here's some others. One thing you'll notice that you should be able to notice is that anytime an object has an axis of symmetry, then the centroid is on that axis of symmetry. And that's basically us. If you want to know how that works mathematically, that's basically saying that when you take when you take your individual moments on either side, as they cancel out when taken about this axis. So if you've got one axis of symmetry, the centroid needs to be on that axis of symmetry. If you have two or more axes of symmetry, then the centroid is located at the intersection of those axes of symmetry. So, just a few other centroids you might be worried about. Arc of a circle, semicircular section, so on and so forth. So again, these ones are used for area. This one's used for area too. These ones could be used to calculate centroids of lines. And I guess they didn't bother to include rectangles, because I think it should be fairly obvious that the centroid of a rectangle is directly in the middle of the rectangle. So what we can do is we can, instead of necessarily having to do annoying integrals for annoying shapes, what we can do is we can basically, if we already know what the, if we already have shapes that we can determine, then we can figure out what the total first moment of area for those for the combination of those shapes would be by adding each of the individual components of their first moments of area together. Then once we have that, we can find our x bar, which is just the location of the centroid for the composite thing, by taking this, dividing by this, and that's how we get that. So